Welcome back to another peaceful journey through the world of numbers and patterns. I'm delighted you've joined me this evening. Wherever you find yourself right now, perhaps nestled in a cozy corner of your favorite room, relaxing in a soft chair near an open window, or maybe lying comfortably on your bed as moonlight filters through the curtains. I hope you'll share your location in the comments below. There's something magical about knowing our shared mathematical adventure reaches across different spaces and moments, like equations floating through the tranquil hours. If these soothing mathematical explorations help you unwind or awaken your interest in the secret rhythms of our universe, I would deeply appreciate a thumbs up or a subscription. It keeps this community flourishing, much like the mathematical ideas we'll discover together. This evening, we're venturing into something that influences every second of your existence, often without your awareness. Advanced mathematics, not the frightening mathematics of textbooks and tests, but the living, dynamic mathematics that explains how your tea warms up, how your pulse flows, how vehicles move, and how nature transforms around you. I hope this journey leaves you drifting toward rest with a greater understanding of the mathematical songs hidden in everyday experiences. Though I should warn you, if these concepts prove too captivating to ignore, at least you'll awaken with a richer sense of the mathematical cosmos embracing you. One quick note before we start. This content serves educational and relaxation purposes only. We're here to explore concepts, not substitute formal mathematical learning. If you're studying advanced math in school, please keep working with your instructors and course materials. So breathe deeply, allow your muscles to soften, perhaps lower the lighting slightly, and let's gently explore the magnificent world of mathematical transformation. The story starts with a fundamental question that has fascinated humans for thousands of years. How do we capture transformation? Not the transformation of weather or loose change, but the exact mathematical transformation that controls everything from the path of a basketball to the expansion of a garden. Long before anyone coined the term advanced mathematics, ancient thinkers grappled with puzzles of movement and transformation. The Greek thinker Zeno created his celebrated puzzles around 450 BCE, wondering how the swift Achilles could ever overtake a slow tortoise if he constantly had to cover half the gap between them. It sounds like a brain teaser, but it was actually exploring the idea of infinity and continuous transformation. Picture observing a snowflake drift down a window during a calm winter evening. Initially, it appears to descend at a steady speed, but with closer observation, you discover something more intricate. The snowflake doesn't move uniformly. It speeds up as gravity draws it down, then appears to decelerate as air resistance builds up, occasionally catching small breezes that make it spiral sideways before resuming its downward journey. How do you express that movement mathematically? How do you describe the exact speed at any particular moment? This represents the type of question that thinkers contemplated for ages, understanding that capturing transformation was essential to understanding existence itself. The breakthrough arrived in the late 1600s, when two exceptional minds, working separately across a bitter political boundary, uncovered the same core truth about transformation. Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany both understood that to grasp transformation, you needed to approach it in a completely new manner. Rather than examining transformation over large periods, they discovered how to focus closer and closer, until they could observe what occurred at a single moment. It was like possessing a mathematical lens that could study the very instant of transformation itself. Newton was driven by the heavens. He sought to understand how celestial bodies traced their elliptical paths, how meteors carved their routes across space, and how things dropped toward Earth. The mathematics available to him could handle steady, uniform movement, but the cosmos was filled with accelerating, decelerating, and curving movements. He required new instruments. Leibniz approached the challenge more theoretically. Intrigued by the geometric connections between curves and their touching lines, both men understood they were examining two aspects of the same mathematical truth: the speed at which something transforms and the collection of that transformation across time. What they uncovered was that these two processes, determining rates of transformation and determining accumulations, were mathematical opposites of each other. This revelation, called the fundamental theorem of advanced mathematics, was groundbreaking. It meant that if you could solve one kind of problem, you had automatically discovered a method to solve the other. It was like realizing that addition and subtraction were linked, but much more significant, This connection revealed completely new approaches to understanding movement, expansion, improvement, and transformation of every type. The elegance of their discovery wasn't merely in its mathematical beauty, but in its universal usefulness. The same mathematical rules that explain the movement of celestial bodies could also explain the circulation of blood through vessels, the transmission of sound waves, or the distribution of warmth through a steel bar. Advanced mathematics became the mathematical vocabulary of transformation itself, able to describe any process where something varies smoothly. And the amazing thing is that this vocabulary surrounds us daily, silently controlling the world we live in. Think about your morning habits. When you pour steaming coffee into a cup, the temperature doesn't cool at a steady pace. It cools rapidly at first, when the gap between the coffee and room temperature is large, then more gradually as it approaches room temperature. This cooling follows Newton's law of cooling, which is expressed by a differential equation, a mathematical statement that connects a quantity to its rate of transformation. The coffee cup resting quietly on your table is actually showing one of the basic patterns of advanced mathematics. Or consider the moment you press the accelerator in your vehicle. Your speedometer doesn't leap immediately from 30 to 40 miles per hour. Instead, your speed increases smoothly, accelerating at a rate that depends on how firmly you press the pedal, the mass of your vehicle, and the opposition of friction and air. That acceleration, the rate at which your speed transforms, is the derivative of your velocity, and your velocity itself is the derivative of your location. The vehicle carries you through a living example of advanced mathematics in action. Even as you inhale while listening to this, your lungs are demonstrating advanced mathematics. The rate at which air enters your lungs depends on the pressure gap between the atmosphere and your chest cavity. As your diaphragm creates this pressure gap, air rushes in, but the flow rate transforms continuously as pressures balance out. The volume of air in your lungs is the accumulation of all those transforming flow rates over time. Your body naturally understands integration, even if your conscious mind doesn't recognize it. When you observe the sun disappear tonight, you're witnessing advanced mathematics in astronomy. The sun doesn't simply vanish at a steady rate. The angle at which sunlight hits your location transforms continuously, creating the gradual shift from day to night. The colors in the sky change and evolve as the atmosphere filters different wavelengths of light, and this filtering process follows mathematical rules that can be expressed using advanced mathematics. The gentle progression from golden hour to blue hour to darkness is a visual display of continuous mathematical transformation. But advanced mathematics isn't only about explaining what occurs in nature, it's also about improvement, discovering the best possible solution among endless possibilities. When engineers create a bridge, they use advanced mathematics to discover the shape that can hold the most weight with the least material. When a bird soars from one tree to another, it naturally follows a path that reduces energy use, tracing out what mathematicians call an optimal curve. When your smartphone's GPS determines the quickest route to your destination, it's solving improvement problems that would have been impossible without advanced mathematics. The more you search for it, the more you understand that advanced mathematics is everywhere, quietly operating behind the scenes to keep the world functioning smoothly. The algorithms that suggest what you might want to watch next on streaming platforms use advanced mathematics to examine patterns in viewing information. The climate models that forecast weather patterns depend on differential equations to simulate the complex interactions between atmosphere, oceans, and land. Even the compression algorithms that let you stream this content in high quality use mathematical methods rooted in advanced mathematics to efficiently encode and transmit data. Grasping advanced mathematics doesn't demand memorizing formulas or solving complex problems on tests. Instead, it's about developing an appreciation for the mathematical patterns that control transformation and accumulation. It's about recognizing that behind every smooth curve, every gradual shift, and every improvement in nature, there are mathematical rules at work. The universe communicates in the language of advanced mathematics, and once you start to hear it, you'll notice its voice everywhere. Tonight, as your eyes become heavy and your breathing slows, remember that you're surrounded by mathematical beauty. The rate at which your body temperature adapts to your surroundings, the way your heart rate slowly decreases as you relax, the gentle curves that light traces as it dims in your room. All of these follow the elegant rules discovered by Newton and Leibniz over 3 centuries ago. Advanced mathematics isn't just an abstract mathematical subject, it's the hidden poetry of transformation that surrounds us every moment of every day. Let's explore what occurs when we slow down and truly examine a single moment of transformation. Imagine you're watching a water drop slide down a window glass. At first sight, it seems to move at a constant speed, but if you observe more closely, you notice something beautiful happening. The drop doesn't move evenly. It accelerates as gravity pulls it downward, but it also feels resistance from the glass surface. Sometimes it stops, gathering just enough energy to overcome surface tension, then suddenly moves forward before settling into a new pattern. This single water drop contains within its journey all the core ideas of advanced mathematics. Its position on the window is constantly transforming, and the rate of that transformation, its velocity, is also constantly transforming. The rate at which the velocity transforms, its acceleration, depends on the complex interaction of forces acting upon it. To truly understand the motion of this water drop, we need to think about instantaneous rates of transformation, the mathematical idea that lies at the heart of differential mathematics. But what exactly does instantaneous mean? In everyday speech, an instant is the shortest possible moment, almost zero time. But mathematically, we can't just set time to zero and expect to get a meaningful answer about speed. If a water drop travels zero distance in zero time, we get the unhelpful result of zero divided by zero. The brilliant insight of advanced mathematics is to approach this problem indirectly, by examining what occurs as we consider smaller and smaller time periods, getting closer and closer to the instant we're interested in without ever quite reaching it. This approach, called taking a limit, is one of the most elegant concepts in all of mathematics. It allows us to talk precisely about things that seem impossible to pin down directly. We can't measure the exact speed of the water drop at a single instant, but we can measure its average speed over very small time periods. And as those periods get smaller, the average speed approaches a specific value. That value is what we call the instantaneous speed, or more formally, the derivative of position with respect to time. Think of it like trying to find the exact color of a sunset. You can't point to a single moment and say there, that's when the sky changed from orange to red. Instead, you observe the gradual transition, noting how the colors shift continuously. The instantaneous color at any moment is the limit of the colors in increasingly small neighborhoods around that moment. Similarly, the instantaneous rate of transformation is the limit of average rates of transformation over increasingly small intervals. This idea of limits extends far beyond motion and into every area where things transform continuously. When a doctor monitors a patient's heart rate, they're examining how quickly the heart beats at any given moment. But heart rate isn't constant, it varies based on stress, activity, and countless other factors. The doctor needs to understand not just the heart rate itself, but how quickly it's transforming. Are the intervals between beats getting longer or shorter? How rapidly is the patient's cardiovascular system responding to medication? These questions require thinking about rates of transformation, ideas that would have been nearly impossible to analyze before advanced mathematics. Consider the growth of a tree in your yard. On any given day, you can't see the tree growing, but over months and years, its height increases dramatically. The tree doesn't grow at a constant rate, though it grows faster in spring and summer when sunlight is plentiful and temperatures are warm, and more slowly in fall and winter. Young trees grow faster than old trees. Trees grow faster when they have plenty of water and nutrients, and slower during dry years. The tree's height as a function of time traces out a curve, and the steepness of that curve at any point tells us how fast the tree is growing at that moment. But the story doesn't end with just understanding how fast the tree grows. We might also want to know how the growth rate itself transforms over time. Is the tree accelerating its growth, maintaining a steady growth rate, or beginning to slow down as it matures? This requires us to examine the rate of transformation of the growth rate, what mathematicians call the second derivative. The ideas keep building on each other, creating richer and more detailed descriptions of how things transform in the world around us. The same mathematical rules apply to population growth. Whether we're talking about bacteria in a laboratory dish, rabbits in a meadow, or people in a city, population doesn't typically grow at a constant rate. Instead, it often follows patterns that can be expressed by differential equations. mathematical statements that relate a population to its rate of transformation. A small population might grow slowly simply because there aren't many individuals to reproduce. As the population increases, growth accelerates because there are more potential parents, but eventually the population might hit environmental limits, and growth slows again as resources become scarce. These population dynamics play out in countless ways in the natural world. Forest fires spread in patterns that can be modeled using advanced mathematics, with the rate of spread depending on factors like wind speed, fuel density, and moisture content. Disease specialists use similar mathematical models to understand how illnesses spread through populations, helping public health officials decide when and where to implement interventions. The recent pandemic brought these ideas into sharp focus, as people around the world learned to interpret graphs showing rates of infection, hospitalization, and recovery. Even in the digital realm, advanced mathematics governs much of what we experience. When you watch a video online, compression algorithms use mathematical techniques related to advanced mathematics to reduce file sizes while maintaining quality. These algorithms analyze how pixel values transform across space and time, identifying redundancies and patterns that can be encoded more efficiently. The smooth gradients you see in digital photographs, the realistic lighting in computer graphics, and the seamless transitions in animated movies all rely on mathematical rules that emerged from the study of continuous transformation. Machine learning, the technology behind recommendation systems, voice recognition, and autonomous vehicles, is fundamentally rooted in advanced mathematics. These systems learn by adjusting millions or billions of parameters to minimize the difference between their predictions and desired outcomes. The process of finding the optimal parameter values involves calculating gradients, multidimensional versions of derivatives that point in the direction of steepest transformation. Every time your phone's camera automatically focuses or your music app suggests a song you might like, advanced mathematics is working behind the scenes. As you settle deeper into comfort tonight, perhaps you can sense this hidden mathematical symphony playing around you. The way your muscles gradually relax, the gentle rhythm of your breathing, the slow cooling of the room as night deepens, all of these follow the beautiful patterns of continuous transformation that advanced mathematics was designed to describe. Mathematics isn't separate from the natural world, it's the language in which the natural world expresses itself, and advanced mathematics, with its focus on transformation and accumulation, speaks most directly to the dynamic, ever-shifting reality of life itself. The story of advanced mathematics is also the story of human curiosity and cleverness. For centuries, people observed transformation all around them, but lacked the mathematical tools to describe it precisely. The development of advanced mathematics represented a breakthrough in human understanding, a new way of thinking about the world that has enabled countless technological advances and scientific discoveries. From the bridges you drive across to the satellites that enable GPS navigation, from the medicines that treat disease to the computer processors that power modern life, advanced mathematics has played a crucial role in shaping the world we inhabit. But beyond its practical applications, advanced mathematics offers something more profound, a way of seeing. Once you understand the ideas of derivatives and integrals, you begin to notice the patterns of transformation and accumulation everywhere. You see them in the way morning light gradually fills a room, in the way crowds gather and disperse, in the way seasons transition from one to another. You develop an appreciation for the mathematical elegance underlying apparently chaotic phenomena. You begin to understand that the universe has a deep mathematical structure, one that humans have only begun to explore. Let's take a moment to appreciate how advanced mathematics helps us understand one of the most fundamental aspects of existence: growth. Growth is everywhere in nature, from the spiral shells of sea creatures to the branching patterns of rivers and blood vessels. But growth isn't uniform or predictable. It follows patterns that can seem random until we apply the right mathematical tools to understand them. Consider a simple example: a savings account earning compound interest. If you deposit money in an account that earns 5% interest annually, compounded continuously, how much will you have after a certain number of years? This might seem like a straightforward percentage calculation, but it's actually a beautiful example of exponential growth, one of the most important patterns in advanced mathematics. The key insight is that the rate at which your money grows is proportional to how much money you currently have. The more money in the account, the more interest it earns, which means even more money to earn interest on. This pattern, where the rate of transformation is proportional to the current amount, appears throughout nature. Bacterial populations often grow this way when resources are abundant. Each bacterium reproduces at a certain rate. So the more bacteria you have, the faster the population grows. Radioactive decay follows the opposite pattern. Exponential decay, where the rate of decrease is proportional to the current amount. Cancer cells, unfortunately, often exhibit exponential growth patterns, which is why early detection and treatment are so crucial. But real-world growth is rarely purely exponential. Resources become limited, competition increases, and growth rates slow down. This leads to what's called logistic growth, where the growth rate starts high when the population is small, reaches a maximum at some intermediate population size, then slows as the population approaches the carrying capacity of its environment. The mathematical curve that describes this process, called a logistic function, appears in context ranging from the adoption of new technologies to the spread of viral social media posts. These growth patterns help explain phenomena that might otherwise seem mysterious. Why does a new social media platform seem to explode in popularity almost overnight, then plateau? Why do forest fires start small, but can quickly become massive, then eventually burn themselves out? Why does learning a new skill feel rapid at first, then slow down as you advance? In each case, we're seeing different phases of growth patterns that advanced mathematics helps us understand and predict. The mathematics of growth also reveals why compound effects are so powerful over long periods. A small but consistent improvement, repeated over time, can lead to dramatic changes. This principle applies whether we're talking about earning interest on investments, developing skills through practice, or building habits that gradually transform our lives. The key is understanding that growth builds on itself, creating feedback loops that can be either virtuous or vicious, depending on the direction of transformation. In the realm of physics, advanced mathematics revealed some of the most profound truths about our universe. When Newton applied his new mathematical tools to the problem of planetary motion, he discovered that the same force responsible for an apple falling from a tree also keeps the moon in orbit around Earth. This insight, that gravitation is a universal force following precise mathematical laws, revolutionized our understanding of the cosmos. The elliptical orbits of planets, which had been observed and described by astronomers like Johannes Kepler, suddenly made perfect mathematical sense. But Newton's laws of motion, expressed through differential equations, do much more than explain planetary orbits. They describe the motion of everything from subatomic particles to galaxies. When you throw a ball, fire a rocket, or simply walk down the street, your motion follows patterns that can be predicted using advanced mathematics. The trajectory of a baseball accounts for the initial velocity, the acceleration due to gravity, and the resistance of air. The path of a spacecraft traveling to Mars must account for the gravitational influences of multiple planets. These calculations, which would have been impossible before advanced mathematics, are now routine. The relationship between position, velocity, and acceleration provides a perfect illustration of how advanced mathematics connects different aspects of the same phenomenon. Position tells us where something is. Velocity, the derivative of position, tells us how fast the position is transforming. Acceleration, the derivative of velocity, tells us how fast the velocity is transforming. These three ideas form a hierarchy of information, each level providing deeper insight into the nature of motion. This hierarchical relationship extends beyond motion to many other areas. In economics, we might be interested in total wealth, the rate at which wealth transforms income, and the rate at which income transforms economic growth or decline. In medicine, we might track a patient's temperature, the rate at which temperature transforms, and whether that rate itself is increasing or decreasing. In environmental science, we might monitor carbon dioxide levels in the atmosphere, the rate at which those levels are rising, and whether the rate of increase is accelerating or slowing down. Understanding these relationships helps us make better predictions and decisions. A doctor who notices that a patient's fever is not just high, but rising at an increasing rate, might take more aggressive action than if the fever were high, but stable. An investor who sees that a company's profits are not just growing, but growing at an accelerating rate, might make different investment decisions than if profits were growing at a steady pace. These kinds of insights emerge naturally when we think in terms of derivatives and rates of transformation. The idea of improvement, finding the best possible outcome among many alternatives, represents another beautiful application of advanced mathematics. In your daily life, you're constantly making improvement decisions, even if you don't think of them in mathematical terms. When you choose the fastest route to work, you're solving an improvement problem. When you adjust the temperature in your home to balance comfort and energy costs, you're finding an optimal compromise. When you decide how to allocate your time between different activities, you're optimizing your personal satisfaction and productivity. Advanced mathematics provides systematic methods for solving improvement problems that would be impossible to handle through trial and error. The key insight is that optimal solutions often occur at points where the rate of transformation is zero. Think of rolling a ball over a hilly landscape. The ball will naturally come to rest at the bottom of a valley, where the slope in every direction is zero. Similarly, many improvement problems can be solved by finding points where the derivative equals zero. This principle has applications ranging from the mundane to the profound. Engineers use improvement to design bridges that can support maximum weight with minimum material. Airlines use it to schedule flights and price tickets to maximize revenue. Doctors use it to determine optimal drug dosages that maximize therapeutic benefit while minimizing side effects. Even evolution can be thought of as a vast improvement process, where natural selection gradually improves the fit between organisms and their environments. Sometimes the most elegant solutions emerge from the simplest mathematical rules. The Brojkester-Krohn problem, first posed by Johann Bernoulli in 1696, asks what is the fastest path for a ball to roll from one point to another under the influence of gravity. Intuitively, you might think the fastest path would be a straight line, since that's the shortest distance, but advanced mathematics reveals that the optimal path is actually a curve called a cycloid, where the ball gains speed quickly by dropping steeply at first, then maintains that speed over a more gradual descent. This counterintuitive result illustrates one of the most valuable aspects of mathematical thinking. It can reveal truths that contradict our initial assumptions. The natural world is full of such surprises. Soap bubbles automatically form shapes that minimize surface area for a given volume, creating beautiful spherical and more complex geometries. Light traveling through materials of different densities follows paths that minimize travel time, creating the phenomenon of refraction. Birds and aircraft achieve maximum efficiency by adjusting their flight patterns in ways that can be described using advanced mathematics. The mathematics of improvement also helps us understand trade-offs, situations where improving one aspect of a system necessarily means accepting compromises in another. In engineering, stronger materials are often heavier, so designing an airplane requires balancing strength against weight. In economics, higher returns on investments typically come with higher risks. In ecology, organisms that reproduce quickly often have shorter lifespans. Advanced mathematics provides tools for analyzing these trade-offs systematically and finding the combinations that achieve the best overall outcomes. As you lie there listening to this, your body is continuously solving improvement problems without your conscious awareness. Your heart adjusts its rate to pump just enough blood to meet your current oxygen needs. Your pupils dilate or contract to optimize the amount of light entering your eyes. Your breathing automatically adjusts to maintain the right balance of oxygen and carbon dioxide in your bloodstream. These biological control systems, honed by millions of years of evolution, demonstrate improvement principles that engineers now try to replicate in artificial systems. The integration half of advanced mathematics, often considered more challenging than differentiation, deals with accumulation and area. While derivatives answer questions about rates of transformation, integrals answer questions about totals. How much distance did you travel during a trip where your speed varied continuously? How much water flows through a pipe over a period of time when the flow rate transforms? How much energy does a variable electrical current deliver? These questions all require integration, the process of adding up infinitely many infinitesimally small pieces. One of the most intuitive ways to understand integration is through the idea of area under a curve. If you have a graph showing how your car's speed transforms over time during a trip, the area under that speed curve tells you the total distance you traveled. This connection between area and accumulation extends to countless other situations. The area under a graph of power consumption tells you total energy used. The area under a graph of rainfall rate tells you total precipitation. The area under a graph of production rate tells you total output. But integration goes far beyond simple area calculations. It provides tools for solving complex problems in physics, engineering, economics, and many other fields. When engineers design a dam, they need to calculate the total force exerted by water pressing against the structure. This force varies with depth. Since water pressure increases the deeper you go, integration allows them to add up the contributions from each small section of the dam wall to find the total force. Without these calculations, dams could fail catastrophically. In medicine, integration helps determine proper drug dosages for patients with varying metabolisms. Different people process medications at different rates, and the same person might process a drug differently depending on their current health status. By modeling how drug concentration transforms over time in the bloodstream, doctors can calculate the optimal timing and dosage to maintain therapeutic levels without reaching toxic concentrations. These calculations literally save lives by ensuring patients receive neither too little nor too much medication. The fundamental theorem of advanced mathematics creates a beautiful connection between derivatives and integrals, showing that these two processes are mathematical inverses of each other. If you start with a function, take its derivative, then integrate the result, you get back to where you started plus possibly a constant. This relationship is more than just a mathematical curiosity. It provides powerful computational tools and reveals deep connections between apparently different phenomena. This inverse relationship appears throughout the physical world. If you know how the velocity of an object transforms over time, you can integrate to find its position. If you know how position transforms over time, you can differentiate to find velocity. If you know how electric field strength varies through space, you can integrate to find electric potential. If you know potential, you can differentiate to find field strength. These dual descriptions give us multiple ways to approach the same physical situation, often revealing insights that wouldn't be apparent from just one perspective. The elegance of advanced mathematics lies not just in its individual ideas, but in how those ideas work together to create a unified mathematical language for describing transformation and accumulation. Differential equations, which relate functions to their derivatives, allow us to model dynamic systems where the rate of transformation depends on the current state. These equations describe everything from the oscillation of a pendulum to the fluctuations of stock markets to the chemical reactions in living cells. Solving differential equations often requires combining multiple advanced mathematics techniques in creative ways. You might need to use substitution methods reminiscent of algebra, integration techniques that transform complex expressions into simpler forms, or series expansions that approximate complicated functions with polynomial expressions. The interplay between these different mathematical tools creates a rich problem-solving environment where multiple approaches might lead to the same solution, or where different techniques might reveal different aspects of the underlying phenomenon. Some of the most beautiful mathematics emerges when we consider systems with multiple variables transforming simultaneously. Partial derivatives allow us to examine how a function transforms with respect to one variable while holding others constant. This is crucial for understanding phenomena like weather patterns, where temperature, pressure, humidity, and wind speed all influence each other in complex ways. Meteorologists use partial differential equations to model these interactions and generate the weather forecasts that help you decide whether to bring an umbrella tomorrow. The mathematics of several variables also underlies much of modern technology. When your smartphone's camera automatically adjusts focus, exposure, and white balance, it's solving improvement problems in a multi-dimensional space where transforming one setting affects the optimal values for others. When GPS systems calculate routes, they're navigating through spaces where travel time depends on multiple factors including distance, traffic density, road conditions, and time of day. The algorithms that power search engines analyze billions of web pages using techniques that extend advanced mathematics ideas to incredibly high-dimensional spaces. Vector mathematics extends these concepts even further, providing tools for analyzing fields and flows. When you see weather maps showing wind patterns with arrows indicating both speed and direction, you're looking at vector fields. The mathematics of vector analysis helps meteorologists understand how these patterns evolve over time, how energy moves through the atmosphere, and how different air masses interact to create storms and other weather phenomena. The same mathematical framework describes electromagnetic fields, gravitational fields, and fluid flows. When engineers design airplane wings, they analyze how air flows around the wing surfaces using vector mathematics. When medical researchers study blood flow through arteries, they use similar mathematical tools to understand how vessel shape affects circulation. When astrophysicists model the formation of galaxies, they apply vector mathematics to understand how gravitational and electromagnetic forces shape the large-scale structure of the universe. Perhaps most remarkably, the mathematical tools developed to study transformation and accumulation have revealed unexpected connections between seemingly unrelated phenomena. The same differential equations that describe the oscillation of a spring also describe the behavior of electrical circuits with inductors and capacitors. The mathematics of heat diffusion through a metal rod also applies to the spread of rumors through social networks and the pricing of financial options. The equations governing wave motion in water also describe the propagation of light, sound, and quantum mechanical wave functions. These connections suggest something profound about the nature of mathematics and reality. The universe seems to operate according to a relatively small number of fundamental patterns, which manifest in countless different contexts. Advanced mathematics provides a language for recognizing and working with these patterns, allowing us to transfer insights from familiar situations to unfamiliar ones. When medical researchers want to understand how cancer spreads through tissue, they can draw on mathematical techniques originally developed to study fluid dynamics. When economists model market volatility, they use tools borrowed from physics. The history of advanced mathematics also illustrates how mathematical discoveries often emerge from practical needs, then find applications far beyond their original purposes. Newton developed advanced mathematics primarily to solve problems in physics and astronomy, but the mathematical tools he created have since found applications in every field that deals with quantitative transformation. Leibniz was motivated by philosophical questions about the nature of continuous versus discrete phenomena, but his mathematical notation and ideas now power computer graphics, medical imaging, and artificial intelligence. This pattern continues today as researchers develop new mathematical techniques to solve contemporary problems, then discover that these techniques have unexpected applications in completely different fields. Mathematics developed for analyzing financial markets has found applications in disease studies. Techniques created for processing digital images have been applied to analyzing biological datasets. Methods for improving supply chains have been adapted to study ecological food webs. The universality of mathematical patterns suggests that learning advanced mathematics isn't just about acquiring a set of computational tools, it's about developing a new way of seeing the world. Once you understand derivatives and integrals, you begin to notice rates of transformation and accumulations everywhere. You see them in the gradual brightening of dawn, the way coffee shops fill and empty throughout the day, the seasonal cycles of plant growth and dormancy. You develop an appreciation for the mathematical structure underlying natural phenomena, and you begin to understand why mathematics has been called the language of the universe. This mathematical perspective doesn't diminish the beauty or mystery of the world, rather, it adds another layer of appreciation. Understanding the physics of how rainbows form doesn't make them less beautiful, it makes them more wonderful by revealing the elegant interplay of light, water, and geometry that creates those perfect arcs of color. Similarly, understanding the mathematical patterns in music doesn't reduce its emotional impact. It helps explain why certain combinations of notes create harmony while others create tension. As mathematical tools have become more sophisticated, they've enabled us to tackle increasingly complex problems that affect human welfare. Climate scientists use advanced mathematics-based models to understand how greenhouse gas emissions might affect global temperatures over decades and centuries. These models consider thousands of interacting variables, from ocean currents to cloud formation to vegetation patterns, and they require some of the most powerful computers in the world to solve the resulting differential equations. Medical researchers use similar mathematical approaches to understand how diseases progress and how treatments might work. When pharmaceutical companies test new drugs, they use mathematical models to predict how the drugs will be absorbed, distributed, metabolized, and eliminated by the human body. These pharmacokinetic models based on differential equations help determine appropriate dosages and identify potential safety concerns before drugs reach patients. In engineering, Advanced mathematics-based analysis has enabled the construction of structures that would have been impossible without mathematical understanding of stress, strain, and material behavior. Modern skyscrapers can withstand earthquakes because engineers use sophisticated mathematical models to predict how buildings will respond to ground motion. Bridges can span enormous distances because mathematical analysis reveals optimal designs that balance strength, weight, and cost. The digital revolution has been powered by mathematical advances that build on advanced mathematics foundations. Computer graphics rely on mathematical descriptions of curves, surfaces, and lighting effect. Signal processing, which enables everything from digital music to medical imaging to satellite communications, uses mathematical techniques related to integration and differentiation. Machine learning algorithms that power recommendation systems, speech recognition, and autonomous vehicles all rely on improvement methods that trace their roots back to advanced mathematics. Yet despite its enormous practical importance, perhaps the greatest gift of advanced mathematics is the perspective it provides on the nature of transformation itself. In a world where everything is constantly shifting and evolving, advanced mathematics offers tools for making sense of dynamic phenomena. It helps us distinguish between different types of transformation: linear transformation that proceeds at a constant rate, exponential transformation that accelerates over time, oscillatory transformation that repeats in cycles, and chaotic transformation that appears random but follows deterministic rules. Understanding these different patterns of transformation can be profoundly useful in personal life as well as professional context. When you're learning a new skill, recognizing that progress often follows a logistic growth pattern can help you maintain motivation during the inevitable plateau phases. When you're saving for a long-term goal, understanding exponential growth can help you appreciate the power of starting early and contributing consistently. When you're trying to break a bad habit or establish a good one, understanding the mathematics of feedback loops can help you design more effective strategies. The ideas of advanced mathematics also provide metaphors for understanding psychological and social phenomena. The concept of a derivative, a rate of transformation, helps us think about momentum in our personal lives. Are our relationships, careers, or health improving or declining? How quickly? The concept of an integral, an accumulation over time, helps us think about the long-term consequences of our daily choices. Small positive actions, repeated consistently, can lead to significant improvements over time. Just as small negative actions can accumulate into serious problems, the improvement perspective from advanced mathematics encourages us to think systematically about trade-offs and to look for solutions that balance competing objectives. Instead of seeking perfect solutions that don't exist, we can look for optimal solutions that make the best possible compromises among conflicting goals. This mindset can be valuable whether you're planning a career, managing a household budget, or deciding how to spend your limited time and energy. The mathematical idea of limits offers a way of thinking about goals and aspirations. We might not be able to achieve perfection directly, but we can often get arbitrarily close by making continuous improvements. The limit concept suggests that the journey toward a goal can be as important as reaching the destination, because each step in the right direction brings us closer to where we want to be, even if we never quite arrive at some idealized endpoint. This perspective can be particularly comforting when dealing with personal growth and transformation. Instead of expecting immediate transformation, we can focus on consistent progress in the right direction. The mathematical intuition behind limits tells us that small, steady improvements can eventually lead to dramatic transformations, just as a sequence of numbers can approach a limit through tiny incremental steps. Whether you're working to improve your health, develop new skills, or strengthen relationships, the advanced mathematics mindset encourages patience and persistence over perfectionism. The study of advanced mathematics also reveals the importance of understanding context and scale. A function that grows rapidly over a short time interval might level off or even decline over longer periods. A rate of transformation that seems significant at one scale might be negligible at another. This mathematical insight translates into wisdom about evaluating transformations in our personal and professional lives. A temporary setback doesn't necessarily indicate a negative long-term trend, just as a brief period of rapid progress doesn't guarantee continued success at the same rate. These mathematical perspectives can help us develop more nuanced and realistic expectations about transformation in our lives. Instead of expecting linear progress toward our goals, we can anticipate that improvement often comes in waves. with periods of rapid advancement followed by plateaus or even temporary reversals. Understanding these patterns can help us maintain motivation during difficult periods and avoid complacency during easy ones. The interconnectedness revealed by advanced mathematics also offers insights into how different aspects of our lives influence each other. Just as transforming one variable in a multivariable function affects the optimal values of other variables, transformations in one area of life often have ripple effects in other areas. Improving your physical health might boost your mental clarity and work performance. Developing better time management skills might improve both your professional productivity and your personal relationships. Advanced mathematics encourages us to think systematically about these connections rather than treating different life domains as completely separate. But let's step back from these philosophical applications and appreciate advanced mathematics for what it fundamentally is: a celebration of transformation itself. In a universe where nothing stays the same, where celestial bodies orbit stars, where seasons cycle endlessly, where living things grow and evolve and eventually return to the earth, advanced mathematics provides a language for embracing and understanding the dynamic nature of existence. It teaches us that transformation isn't something to be feared or resisted, but something to be studied, appreciated, and worked with skillfully. The mathematical beauty of advanced mathematics lies partly in its ability to find patterns and order within apparent chaos. A leaf falling from a tree follows a complex path influenced by air currents, its own rotating motion, and constantly transforming forces. Yet this seemingly random motion can be described precisely using differential equations. A stock market that appears to fluctuate unpredictably actually follows mathematical patterns that can be analyzed using sophisticated advanced mathematics-based models. Even quantum mechanics, the strange world of subatomic particles, relies on mathematical tools that extend classical advanced mathematics into new realms. This ability to find mathematical structure in complex phenomena has profound implications for how we understand our place in the universe. Rather than seeing ourselves as separate from the natural world, advanced mathematics reveals that we are part of the same mathematical tapestry that governs everything from galaxies to electrons. The same principles that describe planetary motion also describe the circulation of blood through our bodies. The same equations that model population growth in ecosystems also model the spread of ideas through human cultures. This mathematical unity suggests that there are deep connections between all phenomena, connections that become visible when we learn to see the world through mathematical eyes. Advanced mathematics doesn't just describe transformation, it reveals the fundamental relationships that connect different types of transformation to each other. The rate at which a river flows is connected to the shape of its bed, which in turn affects the rate of erosion, which gradually transforms the shape of the landscape. These feedback loops and interconnections create the rich, dynamic systems that make up our world. Understanding these connections can foster a sense of wonder and appreciation for the complexity and elegance of natural systems. When you watch waves breaking on a beach, you're seeing the result of energy that might have traveled thousands of miles across the ocean, shaped by wind patterns, ocean currents, and the gravitational pull of the moon. The mathematical equations that describe wave motion help reveal the hidden connections between local phenomena and global systems. Similarly, when you listen to music, you're experiencing mathematical relationships between different frequencies of sound waves. The harmony and discord in music reflect mathematical ratios that have been studied since ancient times. But advanced mathematics provides tools for analyzing more complex musical phenomena, like how different instruments blend together or how electronic music can create entirely new types of sounds through mathematical manipulation of waveforms. The applications of advanced mathematics continue to expand as we develop new technologies and encounter new challenges. Climate transformation, for instance, requires mathematical models that can integrate information about atmospheric chemistry, ocean dynamics, ice sheet behavior, vegetation patterns, and human activities. These models use some of the most advanced mathematics-based techniques ever developed, running on supercomputers that perform trillions of calculations to simulate how Earth's climate system might evolve over the coming decades. Artificial intelligence represents another frontier where advanced mathematics plays a crucial role. Machine learning algorithms learn by adjusting millions or billions of parameters to minimize prediction errors, a process that relies heavily on multivariable advanced mathematics and improvement theory. When your phone recognizes your voice, when your car's navigation system suggests a route, or when an online service recommends a product you might like, advanced mathematics-based algorithms are working behind the scenes to process vast amounts of data and identify meaningful patterns.